Welcome to VS channel. In this video, I am going to explain the operation of timer A that we use in MSP430 and some other microprocessors and microcontrollers. So this is the basic type of timer. When we observe deeply the block diagram of MSP430 X, 4xs or 5xs, where we have a chance to see the timer A block. The timer A block, and we can provide the details of capture, compare registers also. So this timer A requires 2 capture compare registers or 7 capture compare registers, 5 capture compare registers according to their requirement and according to the particular function. So here this timer A can provide the time interval for the specific applications that is performed by the microprocessor or microcontroller and MSP430 family microcontrollers, and which is having 2 hardware parts, that is a timer block and capture compare register. So here timer block is a main component or main part in the timer A register. So in this we are having TA or register, that is a timer A register. So this register is used for here counting the time or measuring the time. So this is a 16 bit register which counts from 0 to F, that is the 16 zeros to 16 ones that we represent in hexadecimal like 4 zeros to 4 Fs. And here this particular timer can perform counting, either it is up counting or down counting. So based on the selection of the particular bits, it can perform different operations. Then coming to capture compare register, capture compare channel. So here this capture compare register works the same way, the important exception of TACCR 0 register. So here the capture compare register takes the input and recording the time, and that value is compared with a TACCR register. The TACCR register contains the maximum amount of time. So if you want to provide that particular amount of time, the amount of time that we are going to provide for the function that is placed in TACCR register, and then the TAR register starts from 0 and it's go on incrementing. So this particular TAR value is compared with the TACCR register. When these two are equals, then the timer A understands the timer interval is completed, then it generates the interrupt and it restarts the counting again from the 0, right? So that here we have capture compare input and we have compare the current value of TR with a TACCR, and we have a chance to generate the interrupts, and here based on the comparison it can go for the continuous of counting and it deviates the function to generate the interrupt and restart. So that we can see in detail in the block diagram of timer A. So this is the diagram of timer A. Now here we have a clock selector, right? This clock selector select the one of the clock among these 4. That means here the timer A can take 4 different clocks. In that auxiliary clock and subsystem master clock, these two are available in the processor itself, inside the processor itself, but TA clock and IN clock, these two is from external source. These are the external clocks. So here the clock selector is constructed by using of a 4:1 multiplexer. So here the 4 clocks are giving as an input to the multiplexer, that is a 4:1 multiplexer, which provides one output to the divider. So when we observe here TASSCL, this is the control bits. So as we know, the 4:1 mux is having 4 inputs and 2 selective lines and 1 output. So here the 2 enable lines or selective lines, that selective line selects one of the input, one of the data input and provides output. So here by providing of this TASSCL bits as a 0 0, TA clock is provides as a output to the divider, and if it is 0 1, then auxiliary clock is selected and that is given as an input to the divider. Similarly, by giving 1 0, subsystem master clock is selected and that gives input to the divider, and if it is 1 1, then IN clock is selected, that is given as an input to the divider. So here if the auxiliary clock is having 32 kilohertz of maximum frequency, that is a low frequency auxiliary clock here, and that means it can provide 32 milliseconds of time period for the clock. Suppose you required the frequency that is 8 milliseconds rather than 32 milliseconds, then the 32 milliseconds should reduce to 8 milliseconds by using the divider 4. By dividing that 32 value with a 4, we have a chance to get 8 milliseconds as an output. So that particular function here done by the divider. So if it requires, it takes 1 as a divider, that means no changes. If it takes divider factors 2, that means the input of divider is provides output as half of the input, and by taking the factor as a 4, then the divider is provides as output 1/4 of its input, and by taking of the factor 8, the divider is provides output 8th part of input of the divider. So like this, by using of divider, we have a chance to reduce the frequency that is getting into the divider into the required level. Based on the required level, we can set the factor as 1, 2, 4, 8. So here also we have 4 divider factors. To select this particular 4 factors, again we have here IDX also the control bits of divider. These are the 2 bits. If it is 0 0, that is a divider is 1. If it is 0 1, the divider is 2. If it is 1 0, divider is 4. If it is 1 1, divider is 8. And then the output of divider is giving to counter. The counter is counts. It is counts the time, right? That means here it is having the TA or register, that is TA means timer A or means register, timer A register. This is the system bit register. It starts from 0 and then it is incremented continuously to reach the maximum value. So here this particular operation is depends on the register, that is TACCR register, timer A, capture compare register 0, capture compare register 0. So this capture compare register is always contain the maximum value or maximum time period that providing for the function. So that value we are going to kept in TACCR register, and always the value that we are having in TAR and the value that we are having in TACCR register are compared by using this comparator. The comparator takes 2 inputs, that is one from TAR register, other from TACCR 0 register, and compares for checking of the equality. When these two are equal means the timer is reached the maximum value, then it is going to stop its incrementation or its counting. If it is not equal, that means the TR is continuously counting. So if it is not equals, it will continue the counting like this. If it is equals, then it gives a clear signal. Then the clear signal is clears the timer A register. That is TR register is becomes clear, means becomes 0, and it gives a interrupt flag, that is a timer A interrupt flag. So this flag is generated when the TR content and TACCR content are equals. When the equalities occurs, so at a simultaneously it clears the content of TR register, at the same time it generates the interrupt also, right? Now we can see. So here immediately I was given the clear information that this is clock selector. There are 4 options for the clock, that is internal clock, SM clock, A clock. 2 are the external source, right? And we have divider. The frequency of the clock can divide before it applied to the timer, which is extended the period of the counter. We use the maximum factor as 8 when IDX is equal to 1. The counter is used for the counting of time. The initial value of the counter is 0, that is a full range, that is 16 bit range we used. So the minimum value is 0, 0, 0, 0. Maximum value is F, 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 F. And which repeats based on the requirement of the operation. Then coming to TR register, it starts from 0 and it go for up. Then and at what means and which state means it is incremented in upward direction until to reach the value that present in TA CCR register, timer A compare register, right? Capture compare register. And then we have need to discuss, that is TA CCRO, CCR 0, that means timer A capture compare register 0. So which contains a maximum desired value of the counter, and according to the application, that whatever the time is required, that we can place in timer A capture compare register. Then comparator compares the value of the timer A register and timer A capture compare register, and if it is equals, it clears the content of timer A and it generates the flag, that is interrupt flag. And this is the control register. Every timer is controls by using of one control register. So here also it is having the control register. The size of the control register is 16 bit here. So here bit number 10 to 15 it is unused. Bit number 10 to 15 is unused, and bit number 3 also unused. That's why we are shaded this particular area. So these bits are not used for this specific application. And then coming to the bit number 8 and 9, the bit number 8 and 9 is TASSEL, that is timer A source select. So in the block diagram we discussed that. So there we have 4 clocks, that is IN clock, TA clock, A clock, SM clock. These 4 clocks considered as a source for this timer A, and we can select one of that among the 4 of the clocks. So by using this TASSEL bits, which is the 2 bits, by giving 0 0 TA clock is selected, and by giving 0 1 A clock is selected, by giving 1 0 SM clock is selected, by giving 1 1 IN clock is selected. So here A clock and SM clock is the internal clock, and these other 2 are the external clocks. So here always SM clock is available. For that we use SM clock. In defaultly we can use SM clock only. The application is needed A clock or otherwise IN clock and TA clock, then we can move to the particular clock. And coming to another bits, that is IDX, that is bit number 7 and 6 is the IDX. So this particular input divider bit. So this particular divider bit can be used for selecting of divider factor. We have 4 factors here: divide by 1, divide by 2, divided by 4, divided by 8. Like this we have these 4 factors. We use these 4 factors to reduce the input frequency that we are giving to the divider into the required level. Suppose if you are giving the input frequency as 8 milliseconds, 8 milliseconds is the time period. Suppose your function is required only 1 millisecond, then we go for dividing that 8 milliseconds with a dividing factor of 8. Then we get 1 millisecond as the output from the divider that we are use for the specific purpose of application. And coming to the next bit, that is MCX. MCX is represents for the operation of mode. So here the timer A is performs the operation like it counts upward direction, that is up counter, and it counts downwards or upwards, and other is in continuous mode. So like this we have 4 operations. One is it is in halt, means it is stop, it does not perform any operation. Up mode operation, another is continuous mode operation, the other is up or down mode operation, right? In continuous mode it starts from 0 value and reaching the maximum value, and then it restart from 0, again it go for maximum value. It is continuously counting, no need to give any signal to restart. It's continuously counting up to required function is completed, right? If you want to stop, then we can stop this, right? So here if this mode counter bit is 0 0, that is a halt, that is a default operation of halt. That means defaultly the time is off. Whenever time is required, then we can use this particular for the operation. Why? Because suppose if timer is continuously on, whether it is required or not, then we are wasting the power by keep this timer A is on. So that we keep this as a off position defaultly for saving of the power. When it is required, then we turn on this by selection of other 3 combinations. If I select this MCX as 0 1, then that is the up mode where the timer is start from 0, it go for 1, it go for 2, it go for 3, like this it go for maximum value that we are stored in timer A capture compare register. And coming to MCX bit is 1 0, that is a continuous mode. That means its timer A starts from 0 0 0 and it go on incremented up to F F F F, and again it repeats the same. You go for 0 and reach the maximum value, 0 go for 0 increments and reach the maximum value. Like this the operation is going to continue. That's why it is called continuous mode. And MCX is 1 1 means where we have a chance to use this timer A in upward mode or downward mode. So according to the application we can change this as upward direction or downward direction. So that is the use of this MCX pin. And then the second bit, that is TA clear, that is a timer A clear bit. So by setting this this bit as reset, that means 0, the TA register and TA clock divider and counter digression, this all becomes reset. So this is a good idea to clear the counter value. Why? Because suppose if you are kept the maximum value is F 0, then start 0 and reach, then we need to wait. Suppose if the counter function is not required but it's counting from 0 to reaching the maximum value, that is F 0. In between, if you want to stop the operation, why? Because it is not required, then we don't have a chance to stop. But by having this particular timer A clear bit, we have a chance to clear that and the counter is going to stop. So here this bit is used. If it is 1 means this going to clear, if it is 0 means the timer A is not going to clear. And coming to the another bits, that is a TAIE, that is timer A interrupt enable, and TAIFG, timer A interrupt flag. First we can see the function of timer A interrupt enable. So this bit is enables the interrupt, right? Now we have a chance to see the particular block diagram of timer A, where whenever this present value of TR and the maximum value that present in timer A capture register is equals, it clears the TR, at the same time it generates the interrupt flag. Sometimes we have a chance to generate the interrupts after a specific amount of time, that is we can set the time as 10, start from 0, when it reaches 10 it generates the interrupts. That means where we are going to repeat the function for every 10 seconds, that is where we can use timer A, it start from 0 and it reaches 10 value, then it generates the interrupt to start the particular function. Again it start from 0, reach the 10, it generates the interrupt to start the particular function. Like this we can use. So here this particular interrupt is enabled by giving 1. This particular interrupt is disabled by giving 0. And coming to the function, that is TAIFG, that is timer A interrupt flag. It represents about interrupt status, like it is pending or not pending. If this bit is 0 means no interrupt is pending, that is interrupt is serviced or completed. And if this bit is 1 means interrupt is pending, that is we need to provide the service. So this is the operation about our timer A control clock register 0. Now coming to the control register 1. So here, and this is the basic clock system control register 1. So that means here we can see one more point, that is here we can discuss about basic clock system. The basic clock system also provides the same function like general timer A, but the thing is that the control register is different here, and the same time where we have 4 different clocks we are using, but here we are using only and 2 different clocks that we can see now. So here the 7th bit it shows the information about the crystal oscillator is off or on. If this bit is 0 means that particular oscillator is on. If this bit is 1 means the particular oscillator is off. If it is off means that indicates that the microcontroller is not using subsystem master clock and master clock. Why? Because so these are generated by using the crystal oscillators that we use in the MSP430 block diagram. If it is not used means we can take the external clock information as a source for the timer. That is indicated by this XC2 off. Then coming to bit number 6, that is XCTS. So here we have a chance to select whether we are going to perform either high frequency operation or low frequency operation. We use this timer to perform the operation on low frequency and high frequency. If this bit is 0, that means a low frequency operation. If this bit is 1, that is high frequency operation. And coming to bit number 5 and 4, that is DIVAX, divider for A clock. Whenever we are applying the A clock, then that frequency is not sufficient for the required application. That means if you want to reduce the frequency of the A clock furthermore, then we use the dividers. The divider is having 4 different clocks, 4 different factors, same as timer A. That is a divider 1, divided with 2, divided with 4, divided with 8. So if it is 0, 0, then that is divided by 1. If it is 0, 1, that is divided by 2. If it is 1, 0, that is divided by 4. If it is 1, 1, that is divided by 8. Coming to bit number 3, it is unused. That means it is always should be 0. Then coming to bit number 210, that is used for the register select. When we observe the block diagram of MSP430 X4XS, where the timer A with 2 capture compare registers, and 5 capture compare registers, 7 capture compare registers. Like this we have different registers we are having. So these particular bits we are going to use for the selection of a register. So here the internal registers are selected. We have 8 different steps to select the internal registers. So the value of the frequency is represented by this particular registers. If this bit is 0 0 0 means that is a 0th register selected. If this bit is 1 1 1 means the register 7 is selected. Like this we can use this particular bits. Now coming to this basic clock system, control register 2. So this is also 8-bit register. Now coming to bit number 7 and 6 that we use for selection of shorts. So here if it is 0 0 we can use digital control oscillator clock as a shorts of the clock for this basic clock system. If it is 0 1 we can use again digital control oscillator clock for the basic clock frequency system. If it is 1 0 then we can use the crystal oscillator that is present in a inside of the block diagram. And we have two crystal oscillators, that means that generates two different clock frequencies in X5XS version of MSP430. So where it is, if it is 1 1 that is a 1, if it is 1 0 that is a clock 2. And coming to DIV-MX, that is bits 5 to 4, that provides divider for master clock. So in previous control registers where we use the divider for auxiliary clock, but here we use for divider for master clock. So if it is 0 0 it is divided with 1, if it is 0 1 it is divided with 2, if it is 1 0 that is divided with 4, if it is 1 1 that is divided with 8. And coming to bit number 3, that is SELS, that's it, that selects the source. Here selects SM clock, the bit selects the SM clock source. That means here if it is a 0 means that is a DCO, digital control oscillator clock. If it is 1 means that is a SM clock. And here we have a again divider for dividing that SM clock into the required level. So again we have DIV SX, that is divider SM clock. DIV M means divider for M clock. So again 0 0 means divided with 1, 0 1 means divided with 2, 1 0 means divided with 4, 1 1 means divided with 8. And coming to DCOR, that is digital controlled oscillator register, for selection of a register we use this particular bit. That means either register is from external side or internal side. So if it is 0 means that is the internal side, if it is 1 means external side. Like this we use this control register. So this is about time array register. If you like this this particular video, please subscribe my channel, that is VS channel, and provide your like and comment, that will inspire me, and click on bell icon for future video notifications. Thank you for watching this particular video. Thank you.